ladies and gentlemen. I'm happy to welcome you to the next session of today. So I hope you had a very relaxing break. Now it's time for wellness for our scientific heart, soul, and brains. So we will have 5 talks, and let's start with the first one related to fuzzy equivalence relations versus fuzzy metrics, which will be given by Isaac Rainis. Isaac, the floor is yours.
Yes. So, the motivation behind this work can be first found in our uh, our previous paper, in which we looked at spaces that were generated by the equality relations. Furthermore, that is, if for Archimedean and continuous t-norms, we can go from metrics to uh, fuzzy equalities and vice versa using functions that map at the interval from 0 to infinity to 0 to 1, such as additive generators. So there is a sort of a bijection between those spaces. Later on, we wanted to generalize metric spaces in a new direction. Rather than looking at fuzzy metric spaces, we looked at fuzzy equivalent spaces and the topology that it was generated from. Namely, we looked at neighborhood systems. And by creating such topology, we lost information. So now we set 3 goals to accomplish, and they were to prove the topologically the topological equivalence between fuzzy metric spaces and fuzzy equivalent spaces. We wanted to generalize fuzzy equivalent spaces for an arbitrary lattice, and also we wanted to construct a fuzzy topology in Chang's sense. So now that out of the way, we have to look at our preliminaries. And first, we took the definition from George and Vermani for the fuzzy metric, which is a function that satisfies these four properties on the screen. And also important to mention that the star operator is a t-norm in this case. And then we looked at fuzzy binary relations, namely star equalities, and that have these 3 properties. It can be already seen that the definitions are very similar, and and now we can define open balls for each of the spaces mentioned. And already, well, the definitions are similar, and for a more geometric interpretation, we can look at these examples in real number spaces. Let's say that we have a star equality from our set of real numbers to at interval 0 to 1, and we fix the center 2, and we want to look at the values that respect to the center are larger than 1/2. That is, that their similarity level is more than 1/2. So we take an alpha cut of 1/2, and we project the values onto the real number space. So now we can look at the topologies between these two spaces, and we can prove that for a star equality space that is it is uniquely determined by the fuzzy metric M. Moreover, if we define a function such as this one on the screen, then it is uniquely determined. But the problem, well, I wouldn't call it a problem, but if we try to look at fuzzy metrics and we take that they are identical to our star equalities, then that would mean that our fuzzy metrics are stationary. So it isn't a uniquely determined for all fuzzy metrics, but still we can choose such parameters d and alpha such that their topologies will coincide. So the next goal was to generalize star equalities for an arbitrary lattice. So we looked at already existing literature on the subject, and a good point and a good starting point was Hall's article about a, a residual commutative L monoids. And the article offered insights into such structures. And the main goal was to look at our structure interval 0 to 1 with the standard inequality and the T norm, and to generalize it more accordingly. So we already have an RCL monoid, but we can look even further and see that for our structure, it is also integral. That the upper bound also acts as a unit element, and that the lattice is also complete. So we should look at IRCCL monoids in short. So, but it is not enough. We can also look at the property if we have a residuated CL monoid, then also that the distribution of the operator star holds. So we should take also that into consideration. But now, one of the main problems arose that we can't always choose an element such that the neighborhood system property holds. That is, in our main case, when we looked at the interval 0 to 1, if we chose the radius 1, then the open ball would be an empty set. And if it was the only element, let's say the top element, then the property, if we have an open set and the point in that set, then we can't always find such a neighborhood that is inside the aforementioned one. So we need to have such a lattice where we can have a choice in choosing such an element. So first we looked at a lattice which has a subset which is dense, such that for every two elements, the supremum of those would not equal the top element. And we also needed to describe the density that is in the interval from 0 to 1. So there was so we defined star dense sets, and when we defined such lattices, then we could define an L-valued binary relation similar to the fuzzy relation, and we can now look at this relation in the previous example. So we can define the balls, the open balls with the center X and the level alpha, and then we can prove that these balls form a neighborhood system as seen on the screen. So after constructing such a topology, we can look at its main properties, such that it is Hausdorff. If we have a closed ball that now it includes the alpha, so equal or greater to that equality, then it is a closed set, and also that if we have a compact set, then it is closed. Furthermore, if we look at if we define a convergence in such topological spaces using open balls, then we can see that we can prove that the subsequence converges to some point in A, if A is compact. So that was all for point number 2, and now finally we looked at how to create an L-fuzzy topology on our lattice. So first we looked at the definition from Chang, which is that we have fuzzy sets such that a subset of fuzzy sets such that it includes the bottom function and the top function, that it is closed under finite meets, and also that it is closed under arbitrary joins. And then an base of the L-fuzzy topology is such that for every set in that fuzzy topology, it can be expressed as a supremum of the elements from our subset. And finally, a fuzzy point is to be defined, and also what it means for that fuzzy point to be in a fuzzy set. For a visualization, that is when a fuzzy point is inside a fuzzy set. For now we are in the real number space. So let's say X is 0.58 and the alpha level is 0.38. So that would mean that it is inside our fuzzy set. And finally, we need a definition of a base such that we can now find an example of our base in our case. So I won't go into further that. And the main construction is that we look at an alpha level and we take the operation with our star equality, and that's it, because it now suffices the definition of a L-fuzzy topology's basis. And previously we thought that maybe it would suffice that if we looked at only fuzzy equalities, so star equalities, but it doesn't suffice because it is not in the because if we look at two T equalities which value is 1, then the one that is inside the infimum of the two functions, then it doesn't work. It is outside of it. So and the nice visualization of it can be seen on screen. And that's mainly it for the work. So thank you for your attention.
Yes. Okay, thank you very much for this extensive talk on topological properties. Now it's time for questions, comments, remarks. Okay.
I have one question. You consider some balls depending on alpha, and I guess that for a smaller alpha, I obtain like bigger ball.
Yes.
So, but you then consider like for all alpha something is satisfied. Why you consider all alpha? Because the balls are not like included for alpha, is nested balls for different alpha. For higher alpha, you have like smaller balls nested in a smaller alpha. Um, just I'm guessing because this is, for example, true for alpha cuts, but for balls, I don't know.
Hmm. I'm is the question about the
Yeah, the definition of the ball.
okay. Oh, okay. Okay.
Yeah, you fix X and you
Yes.
consider alpha, and now you are going along all Y. And if alpha is smaller, so it means that you can obtain the ball which is not like overlapping this ball for higher alpha, not?
Mm, well,
Because you did.
Yeah, so I understand what you mean. So, but uh, so it not corresponds with the metric space, but it doesn't matter. The topological properties that we for the pole could have for the every point inside the pole, we need to find the radius. In this case, it's alpha to be rather small. But okay, this alpha will be small, will be smaller when the will be larger for the smaller ball. But it's okay. It's only mentally. You want it's not radius. But maybe mentally we could also do it like this: 1 minus alpha, but minus alpha. But it doesn't matter really. The problem is that we could find this alpha to be rather small, but we could always find alpha to make the construction of very small ball.
Because I saw some like definitions of convergences, and there was like for any alpha that something belongs to balls, but if the balls are somehow nested, so then why we consider for alpha?
Uh,
But maybe it's impossible to understand the definitions and yeah.
Maybe if you mean the when you
um, yes.
Yeah, for all alpha goes to L, XL belongs to these balls. And Y consider
it's like a typical definition. So for every alpha, there exists to be inside.
yeah, but if I consider something nested, so I take some alpha, so for higher alpha should be, it's always true. But maybe not. Sorry.
Yes, it's not. It's not. But you understand that we could, in the previous definition, to make the poles like 1 minus alpha. It will be the same. We can do this, and it will be really the same. It will be isomorphic. I'm really happy that the topic is so interesting. Unfortunately, we need to stop now. So thank you very much. Let's thank the speaker. Now I'd like to invite Martin Stepnicka, who will be giving a talk on bridging extensionality and similarity-based reasoning.
Thank you very much. That's not my slide.
Thank you very much. Thank you for introducing me. This is a joint talk with Antonín Dvořák and Balasubramaniam Jairam. One of the questions I once got after my lecture was if I can pronounce it. So it's Balasubramaniam. I hope it's something you will train also very quickly. So we'll be talking about bridging extensionality and similarity-based reasoning, which is very closely connected to the previous talk. At that talk, it was called fuzzy equivalence. Here we call it similarity, but it's basically the same notion. So we'll talk about inference, similarity-based reasoning, Hassan bases, and other things you can see on the outline of the talk. What is the crucial notion when we talk about inference or approximate reasoning, Petra? It's just to wake you up because you will be squared during my talk. Fuzzy rules. The others will suffer as well. The rules, fuzzy rules, because whenever we have reasoning, whenever we have inference, we are inferring based on some inputs, we are inferring outputs with help of some inference engine, but we have to do it based on some knowledge which is stored in a fuzzy rule base. And the question is how? How do we do that? Standardly, I would say, or most frequently, we have a sort of logical inference. So typically it's a fuzzy relational system, but we somehow infer with help of, say, logical reasoning. Fuzzy relation is representing the fuzzy rule base, the knowledge. And inference is then, in that case, a sort of image of a fuzzy set under that fuzzy relation. It can be compositional rule of inference or Bandler-Kohut subproduct. What is usually wanted, what is requested for such a system, there is a preservation of modus ponens. So if the input coincides with one of the antecedents, the deduced output should coincide with the corresponding consequent. Clearly, if you say that if Petra is taking care about the lecture and watching it carefully, she will learn a lot. So if the antecedent is equal to the reality, we can deduce that you will learn a lot. And what we want to also preserve is a generalized modus ponens. So if it is just the input is similar to one of the antecedents, we want to deduce output that is similar to the respective consequent. So if Michal is not to torture that much, just more or less watching carefully, you should more or less learn something new from that lecture. Well, the logical type of inference is, the reasoning is based on logical principles. And the preservation of this similarity is just intended consequence. It's not intentionally stored in the way how we determine it, but it's something like a consequence. But what about if we turn it upside down? And this is actually how similarity-based reasoning came to its existence. In particular, the preservation of the similarity in the core principle of reasoning is how it is defined. And in practice, it's based on three functions. The first one is matching functions, where we measure similarity of the input and consequence. And then by modification function, we modify the corresponding consequent to an output bi prime, where the modification is dependent on the matching of, or on the similarity of antecedent and the input. And finally, of course, we aggregate all such results into a single consequent. So similarity-based reasoning is a sort of new kid on the block, but well, new means like 30 years at least, which is much newer than if we go back to Mamdani-Assyrian rules and this type of inference. But it's a little bit new from the different way of how it is defined. But first, let's set up the formal background. We have a residuated lattice, so we have fixed the operations, mathematical operations we will deal with. We have input and output universes, x and y. This is the structure of if-then rules. So AI will be always the antecedents on the input x is x, and by will be consequence on y. So in similarity-based reasoning, as I said, we have a matching function, which is a function from the Cartesian product of fuzzy sets on x, and it maps to 0, 1 interval. So it gives you a sort of degree up to which the input and antecedents are similar to each other. For example, Morsi and Fahmy define matching function as follows. So you can see that it's a sort of like subsethood. The infimum says that we are searching for the least we can guarantee, the least degree into which the input is a subset of the given antecedent. While in the case of Zarek matching function is nothing else but the compatibility degree is the greatest intersection or greatest element in which those fuzzy sets intersect each other. The modification function is shown on this slide. Simply,
measure the matching function, and then this input of the matching function gets into one of the variables of the modification function, which shows how the consequence should be modified. And usually it's something like implication. Not necessarily. It's not given axiomatically. It's just how usually people do that. And the third one is aggregating all such modified consequence. Usually it's an aggregation operation that is appropriate for the purpose, t-norm, t-conorm, uninorm, depending on the previously used functions. Just the scheme of similarity-based reasoning. So we can set up a similarity-based fuzzy inference with respect to a structure. By this F, everything is determined. Your fuzzy rule-based matching function, modification function, aggregation function. And finally, it immediately defines a mapping from sets of fuzzy sets on X to fuzzy sets on Y. And of course, it applies the theta strategy. So first we infer each rule by rule, and then we aggregate the results. So that was just recalling similarity-based reasoning. And now let's talk about halves and bases, whether we approach it from below or from above. Well, from above is halves, and from below is bases. Similarity is nothing else but a generalization of equality. Thanks to the previous talk, and Reinis, this is the fuzzy equality. You just fix a t-norm, and a binary fuzzy relation is, if it is reflexive, symmetric, and transitive, determines so-called similarity relation. Clear? The transitivity means that X has to be similar to Z, at least in the degree to which X is similar to Y, and at the same time, Y is similar to Z. So it's a nice way how to define transitivity in a, say, vagueness environment. And this determines a similarity space if we take X and S, again, used also already in the previous talk. And the most fundamental example for the Lukashevich t-norm is this similarity, which if you fix one of the variables, will always build you that nice triangle-shaped fuzzy set. Okay, and what is extensionality? Did I have to explain it, or how many of you have never heard about extensionality? Have never heard? Olga, you're expert in extensionality. Okay, just shortly. Extensional fuzzy sets are those that are nice fuzzy sets. Look how they are defined. If you don't like this definition that A is extensional if this inequality holds, let's take a look at it from the classical point of view. Forget about similarity and consider non-fuzzy reading and think that this is equality. It says that if X is an element of A, and at the same time X equals to Y, then, because this is implication, Y is an element of A as well. So for non-fuzzy reading, it says that Y has to be an element of A, at least in the same degree to which Y is similar to X, and at the same time X is an element of A. So this defines actually nice fuzzy sets that gather similar objects. If we don't have a nice fuzzy set, what we can do is that we pack ugly fuzzy sets into a nice one. It's called extensional hull. Don't look at the ugly formula. It's nothing else but that we seek for the least extensional superset of a given set, of a given fuzzy set. So it's just give me something ugly, and I will pack it with the smallest superset, which I do have, and which will be nice. So it's the closest extensional approximation of a given fuzzy set. And Klavan and Castro actually showed that it can be calculated with respect to this formula. And imagine, for example, that we have a singleton, that the fuzzy set that is given to us is just a singleton. Singleton is just flat zero everywhere. At one point, you have unit. So if you calculate this formula over that singleton fuzzy set, what you will get is nothing else but substitution of this crisp point to the similarity. So again, if I take the Lukashevich similarity, I fix one of the points, this A, it will be a triangle around of A. So you will immediately get very nice hull of the crisp set, crisp number, and you get a hull. So you pack it nicely to get a nice fuzzy set. Nothing more than that. Very nice representation of a fuzzy number, by the way. So this is how it looks. If you take this point, this similarity will give you such an extensional fuzzy set. If you get that ugly blue fuzzy set, you can pack it like this orange, according to this orange line, and you will get much nicer extensional fuzzy set. The blue one is not extensional with respect to the similarity. The orange one is extensional. Now let's go to a little bit different perspective, because extensional hulls definitely extend from the width point of view fuzzy sets which we are given. That sentence, it can be too wide. And if we are given ugly fuzzy set, which is wide, too much wide, then it's nothing basically. So what about to apply a sort of dual approach, making narrower fuzzy sets that are nice? So then actually by duality, what we define as an extension base, which is the greatest extensional fuzzy subset of a given fuzzy set. So give me an ugly fuzzy set which is wide, and I will build in between of it or below of it extensional fuzzy set, which will be nice. We can prove that we can calculate it by this formula, which is again dual to the one that was shown by Clavon and Castro. And very clear and immediate conclusion is that if we are given an extensional, this is how we set a set of extensional fuzzy sets, then the extensional fuzzy set is equal to its base and hull. Of course, if it is nice already, no matter if you want to build an envelope above or something below, it will be equal. You cannot make anything nicer if it is nice already. But if it is not nice enough, it looks like this. For example, this blue one is extensional, but definitely to another fuzzy relation. But if you are given fuzzy relation, a similarity fuzzy relation that is that wide, like the orange one, the blue one is not extensional, and this is extensional base. It goes below, and it doesn't reach level 1 anymore. If you are given this blue one, again, it's not extensional, and the extensional base looks like the orange one below. So it depends whether you want to go from above or from below. You always can get it nicer than you had it before. Now, what is the relationship to matching functions? I jumped to something else, right? I was talking about similarity-based reasoning. I tortured Petra because of some inference and reasoning. And suddenly I'm talking about hulls and bases. Let's take a look at it. If you are given a similarity space and we get a fuzzy set that is extensional, then for any fuzzy set, I'm not talking about extensionality anymore. If you're given any other fuzzy set, the Zvarex matching function, which is essential for reasoning, of extensional hull of this ugly fuzzy set and extensional fuzzy set equals to Zvarex matching function applies directly to the ugly fuzzy set and the extensional fuzzy set. So no matter if I make a hull or not, I will get the same result from the matching function point of view. So actually it says that it ensures a sort of indistinguishability. It does not distinguish whether I get ugly or nice one on the input. And I should get the same result. Does something like that hold for subsets or bases? Well, if I'm asking in such a stupid way, definitely yes. 15 minutes. I don't have glasses. I read 15. Okay, I'll speed up. We can get something similar also for this kind of matching function. This DJS matching function. It's like the Morsi and Fahmy, only with a reverse order. We ask how much antecedent is a subset of the input. And we again will get the information or the result that it's not actually sensitive to applying base or not. So now we are coming to the results which are connected to robustness. If you are given such a fuzzy similarity-based reasoning system with this Zvarex matching function, and all antecedents are nothing else but hulls of crisp values, give me crisp points, I will build antecedent fuzzy sets as extensional hulls above them. The matching function, this one, will not distinguish between any input or its hull. And so consequently, the result is the same whether we get on the input hull or the ugly fuzzy set. And for bases, it's the same. If I get this extensional fuzzy set of crisp values as antecedents, no matter if the input is ugly or if it is a base or extensional fuzzy set, again, I get the same result on the inference. So it's really some sort of robustness. I don't care what you give me on the input. I will process and I will get the same output. What is the interpretation? Results of the similarity-based reasoning system with this matching function is independent of whether it processes original input or its extensional hull. So actually, as Clavon and Castro say, imprecision stored in the antecedents is unavoidable. It does not make sense to measure more precisely on the input space. Mostly, if you take this matching function DJS, inferred results is equivalent for the process input as well as for its extensional base. So if we have two, if it is not suitable in the context of narrow fuzzy sets, and we deal with very wide inputs, it can be something that can be dually applied. Let me only show you very quickly. It can be generalized. If we are given antecedents, arbitrary antecedents, I can always build a fuzzy relation like this from the antecedents. And it will be a similarity relation such that every antecedent is extensional. So I even don't have to, by purpose, build antecedents as extensional fuzzy sets. I can always find a similarity to which they will be extensional. And as a consequence, I get a theorem which says that for this way given similarity-based reasoning systems and for well-chosen matching functions, I get this robustness. So I don't care what I got in the input, ugly fuzzy set or a nice fuzzy set. Consequently, the inference is also equivalent side in both cases. Let me jump to one more thing which can be mentioned. For example, here, look at those four fuzzy sets. A1 is nothing else but interval. A2 is this trapezoid, the blue one. A3 is the green one, and so on. And B is orange. This B is an extensional base of all the four fuzzy sets. It's absolutely ignoring if you're trying to make it narrower or not. You can directly use the interval, and then you apply the extensional base. You get the same result. So why would you even try to do some fuzzification on the input? Just put their intervals, apply fuzzy bases, and the inference mechanism process is the same. So for Zadek's matching function, process singletons directly, and we build halves. For TJS matching function, just process intervals directly. Don't try to put there any weird, any unintuitive fuzzification, and then fuzzy basis will make the same job for you. You will simply get the same result. So why would we do it? For future work, we haven't even talked about J and G, right? We have just talked about matching function, the first component. So we'll focus on that, and we will discuss other properties. But mainly, I wanted to ask you for your input. It's highly welcome. What do you think that should be further directions of these research? Now I have these 5 minutes, right? Thank you very much for your attention.
Thank you. So now it's time for discussion, question, and suggestions. Or critics.
No.
Do you really need symmetry in a similarity space? Because there are some situations where the similarity is not symmetrical.
No, as it is defined standardly, it is symmetrical.
It depends.
But
For
you
example,
can drop it. You can drop it.
Yeah, you can drop it.
I mean, in this setting, we just use the standard definition that is, generally accepted.
So,
But you can always play it again that you're dropping some properties and it gives you a little bit more general results. I don't see that big motivation for that, but yeah, you can drop it.
Okay, thank you.
Any?
Just a question. You consider like matching functions, Zadek matching function. There are some other options for this matching function that doesn't like you cannot use like your results and that have sense.
Yep, this is important about you added.
Yeah.
Axiomatically, you are not restricted at all. You can invent any matching function you like. That it can be just a game, artificial game with symbols is another story. So we deal with those that are very closely connected to actually things that we know from the fuzzy relational calculus. That's why it works together. You can recognize compatibility degree and stuff like that because we are just picking those nice ones. But if you go to the literature, you can find very crazy, artificially created just, hey, let's do it this way. You can. Axiomatically, you are not restricted. But then you cannot get the nice results at the end. But this was not a suggestion.
Are there any questions? Okay.
What do you think about possible applications? So how do you think if you want to join your work?
I will a little bit run out of your question. Think about any application of fuzzy rules which you have ever heard about. It's just that you will do it this way. The question is whether it can help you to ensure some properties more easily than in the case of, for example, fuzzy relational inference systems or not. But basically, as you can see which operations we are using, probably we will come to a conclusion that is just, it will become equivalent at many cases. And there are some papers that say that if you well choose some of the attributes of the similarity-based reasoning, it will be equivalent to fuzzy relational system, of course, obviously. But it can, yeah. but from the application point of view, any you have ever heard about that use fuzzy rules?
Are there any other questions, suggestions? Maybe just one closing to sum up. So if you were to indicate what and propositional theorem you showed us, would it be proposition 27 or other? Like what is the most important in your thought?
For me, it's the question, what do you suggest? But yeah, basically this. It says that the inference will be the same no matter if you have a hull of an ugly fuzzy set or the fuzzy set as well, or a base of an ugly fuzzy set or the ugly fuzzy set itself. But it doesn't have any meaning without coming to the interpretation, which is exactly what was mentioned by Michal.
Let's thank the speaker once more. And now we go to the third talk of this session, entitled an implicative fuzzy rule system for river water quality assessment based on expert opinion, which will be given by Martin Zemli.
Hello, let's talk about fuzzy inference and water quality. And let's start with motivation, although the biggest motivating factor is the bottom one. Our idea is to answer the question: how much should we invest in cleaning water or not, based on some payoff value, money. And to do that, well, we need to know what the water quality is. Right now, at the Center of Geology, they do some crisp evaluation. They give you a number, and that's the quality. But if we could do it with fuzzy rules, then we would get more information, and well, money more is better. And let's start with the expert opinion, or how they do it right now. And for now, we are simply looking at the chemical variables values, and the type is simply, it means that we are looking at a smaller river. That's irrelevant. And what I do is they have from very good to very bad, and basically they do measurement and look into which box the value falls into. And for the final evaluation, they simply do one out, all out principle, which basically means they look at the worst one, and that's the final one. Okay, but how to go fuzzy? Our previous work was basically we made a Mamdani system because we didn't know how everything works in that direction. But during ELSFOT now last summer, we were asked about some nice properties, whether or not our system has them, and so we changed our mind because for the Mamdani system we couldn't find nice results about monotonicity. And let's speak about coherence. Because for coherence, well, the consistency of our system, we want that for our input x's, we want some y such that the relation gives a value of 1. So now if we look how the Mamdani system looks like, the issue simply is because we aggregate simple single rules using maximum, which means, okay, if one of the rules reaches value 1, well, now we have value 1. So the definition, well, doesn't make much sense. So implicative model it is. And as a side note, we used only the Lukasevich T-norm and the corresponding residuated implication, and we did not play around with them. So the big question is, okay, how can we go fuzzy? Because we had some crisp data, and the answer is quite simple. We simply took the same intervals and drew a triangles on top of them. And for the leftmost and rightmost values, because we had simple inequality, not an interval, we simply extended to some amount because the whole intervals were already uniform. So we assumed that it would make sense. It's still uniform. And for some extreme cases, we just map them back. Okay, but what next? We have our input our input dimensions, membership functions, we need to make the system. Let's start with monotonicity. And luckily for us, Martin Stepniczka and others already made all the required results and requirements for us to have nice properties. So what's left for us is to say thank you and put everything simply together. And for that, we need some simple definitions. When I speak of monotonicity, I think of we have some fuzzy number. We defuzzify it. So we want for the defuzzifying function, the final output to be monotone. And we need, well, the first of maxim is the first of maxim, and the same is for the. And for the we also need modifiers for the membership functions. And to better understand the definitions, let's just look at an image. For the at least modifier, we have some fuzzy number, and the modifier simply, in simple words, we simply go either up or stay the same. And for the at most, we just flip mirror image from the other side, nothing too much. Okay, but why do we need them? Let's look at the single rule. We have our membership functions for input dimensions. For us, it's in 5 because we had 5 measurements. And then based on these permutations, we map them to consequent. And because we had this one out, all out principle, this mapping is simply maximum of these, because for each index, the less, the better quality. So the more, the worst quality. And to apply the modifiers, we simply draw arrows where it's required. And why do we do this? It's 2 more blocks away. And we can define the at least fuzzy relation, which is we take all the individual rules and we aggregate using minimum. And we can do it the same thing for at most and put them together to get at least at most, which is take these and take and, which leads us to the result for monotonicity, which basically says if we add the modifiers and we have coherence, we get monotonicity. But hey, but do we always get coherence for free? No, that's why we need to reference another theorem, which basically says if the membership functions for the consequent form an M-strong covering, then we also get coherence, which basically means, because we have a linear order of quality, which means that for the membership functions and distance M, so between their cores, we want that the sum of the values is just more or equal than 1. And the same is for less than M, which in our case is not too hard to acquire. Another thing, we want continuity. And it's even simpler to get that one. We could either cover the input dimensions, but because we want Ruspini's condition to hold, we can't really do that. So we are left with the other condition. We want to use membership functions such that they would cover the whole space, which if we simply use Gaussian membership functions, we get it basically for free, except we would have to play around with them because we want them to be high, well, wide enough so that they would be high enough so that we would have our M-strong covering. Putting it together, we have our functions for the consequent, membership functions for the consequent. I already spoke with my supervisor. She said it's all fine because mathematically it makes sense. But for me, I feel like we should add more functions simply because otherwise they are all pushed, like squeezed together. So when we perform inference, it feels like there isn't just enough space to really distinguish between cases. Because if you look at the same example, to me, because we haven't really worked on this field that much, it feels like we probably should add more so it would look prettier. And the other question was, okay, how can we, based on water quality, we would like to know how much we would get if we cleaned or couldn't clean the water body. And for that, we can simply define a simple number payoff function such that we have some cost. It's a triangle number. This is cost if our water is clean and the cost for cleaning the water. So basically, if we don't clean, we gain n times the better quality, the more, or n minus the cleaning costs. So the worse it is, so we assume the more we have to clean. And if we put our previously acquired membership value, we gain these two, which is for not taking action and taking action. Probably you can't see the values, but and because we have a discrete problem, it wouldn't hurt to simply choose the most based on the falsified value. You could notice that I'm using the center of gravity, but I only had the nice properties for mean of maxima. So why is that? So we played around a bit more. So what happens if we introduce more uncertainty into these values and also change this to 80 so that it will be closer to 100 and would have nicer plot? Because okay, yes, we didn't change the core, so it's expected that the mean of maximum will stay the same, except for the center of gravity, where the more uncertainty is, the more it can change. But it's no secret that our main idea is to introduce the notion of a value of information, and our idea was to, is there a way to somehow compare two cases where we first optimize and then defuzify, or defuzify and then optimize? And the issue then is that if you have way too simple functions that for mean of maximum, we can get that they are the same, so that can complicate the way how we define. So we would either have to find, I don't know, like stronger examples where we get something nice, or we could play around with center of gravity, which is what we did, except numerically, to check whether or not the same system is monotone with respect to center of gravity. We simply check it numerically. We sampled 1.x2, and then we sampled another one such that it is less in every dimension, and then check whether or not after throwing both points at our inference system, the inequality would hold. Luckily for us, it did. Well, it hasn't failed yet, I should say. And another issue is that if we go back to our data, it is not uncommon that there is some issue with nitrogen in Latvia, and for nitrogen it's really bad, while for others it's really good. So why am I telling this? Because another issue what we are having is that for all bad or all but one is good, I should say. That the system doesn't distinguish them. But if you look at the intuition, it would make sense that water body that is all bad would cost less, no, would cost more to clean instead of the other one, which we did slightly discuss with my supervisor Olga, that this is the issue because of the way we aggregate rules, which is the minimum, because in that case we sort of lose the information, the distinguishability. So we should generalize it to a T norm instead of minimum, but that would imply that we would have to go all the way back and check the monotonicity, rules, continuity, and coherence, and so on and so forth. Well, although I already mentioned the conclusions, it's about whether or not we should add more membership functions to the consequent, which is more or less like a cry for help, because we are not familiar with the field, so suggestions are nice, we like them. And there is the second one is, I feel it's not really a question, it's because I feel like we ourselves don't really know what would be the next step. So it's like floating. Maybe Professor Asmus, she will be presenting the same topic, not the same, but the optimization and value of information on Thursday. Maybe she already knows the answers, and we should just speak with her. And the third one I already mentioned, so that leaves me with thank you.
So thank you very much for the talk. Now it's time for questions, discussion, suggestions. Let's switch to marks. Maybe I will start with one very philosophical one. When looking at the title, I started to just maybe naively wonder what is the in water quality problem you handle, like is the fuzziness somehow integrated in this problem that you consider to this, well, to stick to fuzzy inference? Like for the motivation, I would like to ask.
I feel like that was the intuitive first option that we chose, and then we just stick to it.
Okay.
So I can't like if you would say there are another better alternatives, I wouldn't be able to argue with that.
Okay, I just wanted. Okay. Then
I'm not sure if I got it all. So you have your antecedents are triangle.
Yes.
Your consequence are Gaussian shaped
Yes.
sets. And you ensure coherence.
We played around with the coefficient that whose name I forgot, the scaling one in the Gaussian function, so that they would be wide enough so that they would be high enough for the strong covering, which gave us coherence.
So okay.
So the answer would be yes.
So then okay. Then I'm really surprised that you get this type of output fuzzy sets on the output which you showed. Because at the end, one of the last slides you showed, if I got it well. Yeah. Okay.
This one?
Yeah. How do you get them?
Because you map all of them to the worst one, so it keeps the worst one. So because
So it's okay. So this is only in the corner of the fuzzy rule base.
yes, because
If you showed output from the middle fuzzy rule base, it would look differently, right?
yes,
Yeah. Okay. Okay. Yeah. Now I get it.
when you minimize, there will be 1, 0 that just cuts everything off.
Okay, but here is the problem: the center of gravity is like averaging it too much, which you can see that it's going to be very close to the middle.
Yes.
Okay. Yep. Now I get it. Thank you.
okay, we have one more question.
There can be various requirements on the rule base, but I'm surprised why you require this coherence. For me, my approach is practical. Do inside whatever you want, but we reach reasonable results. And I don't see a motivation of the coherence assumption.
I think the way I understand is the motivation for coherence simply is the monotonicity, because it is nice to have such that the system is monotone and it doesn't do some non-monotone things. So just
I can comment a little bit because it comes from our papers which we have with Balu and with Bernard. First of all, you should impose coherence as something which guarantees you that you don't have inconsistency in the rules, that they are not actually telling you at the same time go to the left and go to the right, because then you have to physically split yourself into two pieces, which hurts. And here in this case, when you want to ensure monotonicity, it's very comfortable technical tool. You said you want to be practical. If you keep the coherence, then you focus only on the core of the output fuzzy set, and you just defuzzify by going to the left, taking the left corner, right corner, and making average. While if your fuzzylation drops to lower values, then it's very technically difficult to find a way how to defuzzify it, and you're actually tortured by the computational complexity of the inference system. Did I answer your question correctly? Thank you.
So let's thank the speaker once more. Okay, so we've seen results from Riga. Now we travel a little bit geographically back to where we are. And the talk will be given by Michaela Brutenichova, entitled Fuzzy Relations in Some Decision Making and Expert Systems. Oh, at the beginning, I need to say that there are so many expert system approaches and applications and papers and so on. And it's very easy to be lost in it. And it happened also to me. I got lost in that papers and so much things. So it doesn't matter. It's happening. It's the experience.
I will find myself in the future again. But what I decided to do, I decided to have a look on the basic theory, which is the core of lots of things which you were talking before. And I think that this presentation is going to be light and refreshing, maybe, that it's not going to be very difficult. But it's only the consequence of very difficult times of me. So, but it's not so visible here, but it's. So why I was interested in expert systems? Before that, maybe last year or 2 years, I was studying linguistic variables and modifiers. So the linguistic variable is a variable which values are linguistic terms, and linguistic terms are modeled by some fuzzy sets, classical fuzzy sets, interval value fuzzy sets, what you are able to imagine. And when we have some transformation, when we transform one fuzzy set to another fuzzy set, and it makes some sense in the context of these linguistic variables, then we call it that it is a modifier, and we use it. Also, it was in previous presentation, there was high and very high and bad, very bad, and this is the modifier of the set. I studied this type of modifiers based on relation. It's a specific construction. Here is the, I don't want to turn it off. Okay. Here is the relation, here is some mapping, this conjecture, and supremum over the elements of X. It works pretty well. It is written in this paper. This is expensive under some conditions. This is restrictive under some conditions. The shape is very nice, but it's still a linguistic variable. We also have some results about it and so on. But the question is it possible to use it also somewhere in some different place? And it was I wanted to try to find some application in expert systems, not exactly this construction, but something if I create some other construction similar like this, if I am able to compare it to some different application in expert systems. And it was the problem that there were so many things. So I started to read about expert systems and so on. Expert systems are the very important tool for decision making, where the human reasoning is imprecise and so on. Also, expert systems are designed to imitate the way experts solve problems by working with structured knowledge. This knowledge are represented by fuzzy rules, and these rules could be some if-then statements, which are talking about what decision should be made. So it is refreshing in this style that I am talking about basic things, which you maybe know. So next, the core of an expert system is the inference mechanism, which applies the rules to the available data in order to reach conclusions or recommendations. An important aspect of modern expert system is that they should be explainable. It's not important only to know the decision, but also how the decision was obtained. So it is this part of expert systems. And fuzzy aggregations play also the key role here, as they combine information from multiple rules and criteria. One example of expert system is fuzzy regulator, which I wrote here, that there is fuzzy regulator, and they are used, their application of them, or they are part of something, is probably washing machine. You know this application. If you have lots of clothes, it's heavy, and it determines how many washing powder it needs to use. And there are also lots of many different applications. So this is something about expert systems. What next? Relation, crisp relation, classical relation. You know it, you use it. Do you remember the definition with terms of set theory? If you have the element set and to be element of the set, 3 terms. And it's possible to build definition of relation with these 3 terms in some way. So I want to refresh this knowledge of you. So if we have definition of order pair with these 3 terms, if we have ordered pair, it is a set, classical set with two parts. In the first part, you have a set with two elements, which are in this ordered pair. And in the second part, you have the second element of that pair. So you have some construction of the set and it is ordered pair. An arbitrary set of ordered pairs is a binary relation between x and y. When the first element is from x and the second element is from y. I was teaching it the first year students at the university and it's very nice. So I like this definition. And if we define also a relation to be a subset with these three terms, which I mentioned before, and also the Cartesian product, which is the set of all ordered pairs where the first element is from x and the second is from y, we have also the relation. And what next? We are able also to define mapping with the help of relation, and it is the relation which satisfies this condition. If for every x there is at most one image, then this relation, we can call it that it's mapping. So it's nice. Every mapping is a relation. And for us, this is also friendly form, I think, from analysis that it's mapping from Cartesian product to Z01, which means that if this element has value 0, it is not in relation. If it has 1, it is in relation. So we work in fuzzy setting, so we use interval 0, 1 instead of this set. And I will use these notations. I am sure that you are familiar with this. So no. And what next? What is the role of relation in decision making? It was also said before that it is used for modeling the rules. So if we have some rule, if x is a, then y is b, then we use relation as a modeling of that. And we can use lots of some options for it. The most used is they are here. We can use implication or we can use the norm. So we have some relation, which is a description of the rule. What next? We need to build a fuzzy inference mechanism. This fuzzy inference mechanism is the bridge between information and formal decision. I think your picture was better, but it's something easy. So what about fuzzy inference? The compositional rule of inference is the most used, is the most famous inference mechanism in fuzzy expert systems. It derives the conclusion by combining fuzzy input with fuzzy rule using some selected t-norm. T-norm models logical conjecture and also determines how strongly the rule is activated. Here, the comma doesn't mean negation. It is a notation for observed A. So this AB is from previous slide. It is in our rule. Here is our observation, and here is our decision. This very interpretable and flexible approach. So what next? It's not the same, but it looks similar to this construction. We have supremum. Here is the mapping some t-norm, but t-norm is a special case of conjecture. Also, t-norm is commutative, so we can change the order of it, and we have relation on the first place and this is on the second. And also, that's it. Here we have xy, and here we have only xx. And also the input to the relation is different. Here it is element x and y, and here it is values of how the degree of x, if it belongs to A or not. But it looked familiar. It was interesting for me that probably it can make some sense or not, but I didn't find anything that. And so we have some fuzzy rule. The fuzzy rule can be modeled by implication or T norm. So use the T norm. Here we use minimum and here is arbitrary T norm. If it is also minimum, there we have a special case and the name is Mandani inference. It is here. So what can happen if we use minimum also here and here? Probably it is not a good strategy because here we have values x and y, and here it is these totally different values, and it doesn't make sense. So it is not good to try to generalize these things to this modifier, but okay, it looks similar. I wanted to talk about something to refresh some memory. What else? What can I do? What more I can do? So I can study more relations with some different properties or some special construction or something, and there are so many options. There are so many properties of relations. Some of them are written here, but not all. So these properties defined other relations, for example, similarity, inclusion, order, equivalence, preference, and so on and so on. Resemblance is the approximate equality. I will talk about it later a little. Nearness, it talks how near the element is to the other element, and so on. So it's very wide. There are so many relations. It's very difficult to choose one, which is correct. So usually there is a process that I choose some, and it's like also it was this way. I choose the preference relation. So it means that I have some value for AB, and it is like A is preferred over B. If it is 1, it's great. If it is different version representation, which I had, okay, there was AB and it was AB2, and this line is going to be here, but it is not in presentation. But it was different 1 hour ago. Okay, so there are mistakes in these positions. And there are also properties which usually holds for preference relation, that it is some symmetry over diagonal, that the sum of these elements is equal to 1, and also transitivity holds. This is very natural relation that we have some experts, and I want to tell that this is better than this, that this is better to this, but not from this, and so on. So it's possible to gain it some way. But there are lots of ways how to have this relation. So what more? I have a relation, and what next? I can use some aggregation and gain some decision. There are probably many ways how to do it. Or I can create some score for every element and then choose the max. It's only examples of some ways, nothing specific. The question is if I am able to use preference relation also for my modifier, for our modifier. And this is something like motivation that we have experts. I have preference relation for the experts. I have some other preference and so on. I have also their decisions. And I choose the one expert and I want to modify his decision, but I want that decision is influenced by experts who are important for me. So this is some idea, and we try to construct something for it. So what is happening here with preference relation? Necessary to say that nothing nice, I think, because lots of nice properties holds when R is reflexive relation. So there is 1 on the diagonal, not 0.5. And also if C, that conjecture is a semi-norm. So it has also these boundary conditions, which depends on the value 1, which is here in this relation. And if it is not satisfied, this pretty wild, it's not nice, it doesn't make sense. If I use some classical examples. We have some result that if this is a semi-norm and this is a relation like nearness, so there is one on the diagonal and it is slowly decreasing to the sides. So it is respective to the order, then convexity holds. And it's important for decision making and so on, but it's difficult to interpret it. If the relation is different from me, is different. So it's not so universal attitude, and this result is not very applicable for that. So what next? If it is not working, we can create something different. We can use something different instead of supremum or infimum, or instead of this mapping. We can transform the relation in some way to gain something that is more useful. And I think it's for future if I will be successful in this. And this is all about my troubles during last weeks. So thank you for your attention.
Thank you very much for your talk and also the honesty. And also at the beginning, I was feeling like a student, so it was very a nice experience. Questions, remarks, comments? Okay, I will have one regarding the modifiers. So when we have big and very big, it's a very natural connection to, let's say, linguistically. But what if we have big and large? Is it also like implicit that we apply the modifier? Can we treat then the large as a modifier?
Yeah, it can be very big. It depends on the setting which we choose.
But on the linguistic side, are there like
I think
references that
Lots of English or Slovak language is not the same exactly.
yeah, that's why.
No, large is something different as big. Large lake, but it's not big lake or something like that. I don't know. It's not the same. It's not modified value. Big, very big. Large, very large.
All right.
Maybe it would be nice if you somehow made a sort of like classification of modifiers, those that, for example, having this narrowing effect. If you have very big, very large is narrower than original large or big, right? But you can have also widening effect, more or less roughly. If you say that somebody is small, but he's roughly small, then it allows him to be a little bit big, still small, but not that much small. And then it can determine actually the shape of the fuzzy relation, because then the fuzzy relation is nothing else but a matrix of values, and it has to be somehow monotonic in some way to be narrowing or widening. And this could be a sort of like advice which guides you which relations are doing the job you expect them to do. Because basically, you compare two formulas that's the same. Still, it's just an image of a fuzzy set under a fuzzy relation, and the fuzzy relation does the job. Either you have it axiomatically given that it has to preserve some properties, or you just get it by constructive approach. Fuzzy rules is construction. You just put antecedents, consequence, put their operations, but altogether what you get is again a fuzzy relation, which was somehow constructed to store the knowledge. But still, the fuzzy relation is sort of memory, which keeps the way how something will be modified, either input to output or a fuzzy set to modify fuzzy set. Fuzzy relation is the core, and just try to maybe determine what the modifiers should do and what are type of modifiers, and it could lead to economic restrictions on the relations to do the job.
Thank you, Martin, for this excellent suggestion. Are there any other questions, comments? Okay, so let's thank the speaker once more. And now I'd like to invite the last but not least speaker of today, Vladimir Yanis, who will present us the relational modifiers and Delphi.
Thank you. Thank you. Okay. My talk is a joint work with Francisco Javier Talavera from the University of Pamplona of Navarra in Pamplona in Spain. And I will speak about modifiers maybe in more details in this talk. I hope you remember one of maybe the first image that was presented by Michaela. There was a fuzzy set old, and then a fuzzy set very old. I'm grateful that she did not use any numbers in that image. So that was a relatively classical example of a modifier. That means an expression that alters the meaning or the scope of a value of a linguistic variable, I would say. There is a lot of work about modifiers, and one of the initial works that is somewhere on the verge between linguistics and logics was published in 1973 by Lakoff, and this is an extract of that paper. Citation will follow soon. Now you see a lot of linguistic constructions that can be used as modifiers. Some of them can be understood as you said, widening or extending, but some of them can be represented by one of these categories, like par excellence or basically all but virtually, and so on. And so there are many cases. So now some terms. A linguistic variable is something that has values, the temperature, age, distance, and so on. So and values are some like cold, medium, hot, and usually they are or they may be represented by fuzzy quantities. And modifiers change the shape of these quantities, and as you can see here, like very hot, it can be used in different ways. Here are two possibilities, like hot at point t minus t0. T is the temperature, okay, or square root of hot. So both of them are meaningful, but they are different. So okay. Here's the citation. Lakov. It's a long and extensive and nice paper as a about linguistic hedging. There is also a nice paper by Willem Novak, Comprehensive Theory of Trichotomous Evaluative Linguistic Expressions. Also, and what is especially for my interests, the most important direction of research are linguistic modifiers and especially relational modifiers. These are modifiers based on some relation among the elements of the universe. Yes, you have a universe, and there is a relation among the elements of the universe, and the modifier takes somehow into account, I will show how, this relation. So, in that paper, Kera and de Kock define a modifier as an arbitrary mapping from the collection of all fuzzy sets to the collection of all fuzzy sets, which is, I hope you will agree, too wide definition. So, not any such transformation we would call really a modifier. So that's too wide. So we usually have some additional requirements for a modifier, like being expensive or restrictive. Yeah, that's what was mentioned in the discussion to the previous talk. Or modifiers with pure pre-modification or pure post-modification. It depends on their expression as a composition with some real function, either from the right side or from the left side, and especially the two cases with hot. One of these was of this type, and the other one, the square root, was this type. Yes. So one was first we shift the fuzzy quantity, and that's and then apply the fuzziness, or we apply and multiply, take the second power or something, some function. And the relational modifiers, these are modifiers counting some binary relation on X. Terra and the Coq define two types of relational fuzzy modifiers. One is defined by a conjunctor, and one by one class by an implicator. And these are the definitions. So in conjunctor-based modifiers, we first find the values of the A is a fuzzy set that is going to be modified. R is the relation on the universe, and C is a given conjunctor, and this is the way how X is being modified. Yes, this one. Or the same with implication, but here we take infimum. We can interpret this in a quite natural way. We have a set of evaluators, X, some people who evaluate some product or service or whatever. AX is the statement of the evaluator X, and RXY is the rate of influence of X upon Y. How important is that person for that person? R is, it's natural to take R reflexive because I believe in myself. I'm consistent with myself. And it's possible to show that RC, if C is a conjunctor, then RC is always an expansive modifier. If I is a border implication with, this is the property, then RI with the implicator-based modifier is restrictive. So this, this system of discussions and approaching the common result in evaluation process is called a Delphi method. Delphi method, what does it mean? It means that people are going to discuss about something. These people here. They decide somehow, and each of them then reveals his or her decision. Yes? So the people say that I decide that I assign 10 points because of this and this. The other person says, I assign only 4 points because of this and this and this. So these evaluations are public, and people know each other. So, for example, because then there is the second round of evaluation when they can either keep their original evaluations or change them, and it is possible that they change their evaluations based on the others' evaluations. Because, for example, this man respects this lady, And if her evaluation was high, then maybe also he will, in the next round, he will increase his evaluation. Of course, that's the effect of the relation. Of course, the relation need not be symmetric because it may be that this lady has not too good opinion about this person, so his evaluation, she doesn't care too much. So the relation are should be reflexive, but by no means symmetric. So they decide, and then they review the decisions, and then there is a repeated evaluation. And this can be done several times. If there is enough time, then infinitely many times. And we have a process of repeated evaluations. And what might be interesting is to ask the question, what is the final evaluation? What is the limit of this process? So as a modified value, we can decide how to do it. This is the weighted sum of evaluations, where the values of the relations are the weights. So if we use this, I mean it's only okay. If we use this, then I will show you a simplified case with only two evaluators. So we have this system of equations that is going to be repeated. So this is here, it's in matrix form. Because of the time, I will skip it and just come to a conclusion that finally this was just to impress you. No, yes, this is the final result. So we obtain this as a final value of these two people, the limit value. There is also, of course, another way how to do it, because practically, if we have to decide about something, it is not very natural to think that I take into account your opinion and then I decide. No, usually I find something that I respect too much, and I'm interested in his or her opinion. And that's so let's call it the best friend method. Everybody has some, at most one best friend, and his or her opinion is important. So this is the modified value, but the original value plus the difference between my best friend's opinion and my opinion multiplied by some weight beta. And the result is here. It's weighted sum. Of course, this is just for two people. For more than two people, that's not finished yet. There are some open questions, but we can at least what we know, that if there is a chain that this is best friend of A1, this is best friend of this person, this is best friend of this person, and this last person has no best friend, that's an easy case. Or if there is a loop of best friends, or if there's a chain and then a loop. So this can happen, these three cases. In the first case, finally, all the people accept this opinion. In this case, a loop, there is some kind of a mean. It's not a weighted mean. That is the limit value. And in this case, the limit value is that mean of this circle, and all these people obtain that mean. Thank you.
Thank you very much. Thank you. Okay. Yes, thank you very much for this very interesting talk. Now it's time for questions, suggestions, comments. Okay.
You showed us that there is a limit, but probably you have to add some additional constraints. just because why should we believe there is a limit? Maybe we are going around.
Yes, thank you. That's right. There is not always a limit. There is a constraint on the weights. For example, I know that even computationally I have made a code in Python and not always it converges. But for example, that's the open question. I'm almost sure that if the weights are small, I mean that the sum is less than 1, then there is a limit. But I have not a proof. It's just a hypothesis. Thank you.
Thank you. Other questions, comments?
Thank you very much. If you can go to the previous slide. Can you tell once more if there is a difference between the results of chain and the loop? Like a loop, the limit value is a mean,
Yeah.
and the chain with the loop is all except
This is
mean.
A1 has a best friend, this best friend. A2 has this best friend, and so on. K minus 1 has this best friend. This person has no friends. That's a chain. A loop is that there is a loop. Sorry, these dots should not be here. AK's best friend is A1.
No, I understand this. I'm asking about limit values. So for the loop, it is a mean, and for a chain with a loop.
Oh, it's not it's under as the previous discussion. Sometimes it doesn't converge. If it converges, then that is some kind of a mean, but not an arithmetic or geometric, some mean, but I don't know which mean. So it's something between the smallest and the largest evaluation, something in between. Not a mean in a narrow sense.
No, okay. And is there a difference between a limit value of a loop and a chain with a loop? Because you write a mean and then you write all except the mean. So for me, it's the same, but so I don't see the difference.
There is not much difference.
Okay.
This is just a loop like this. This is a chain and then a loop. Okay.
Yes.
So that's the only difference. And if the weights are good, I mean, maybe small, then the limit is that unknown mean of this loop, and all these people in the chain obtain the same value.
Thank you.
I hope it's clear now. Yes, exactly.
Okay, thank you very much. Are there any other questions? Okay. So let's thank the speaker once more. And this concludes the session. So let's give a last thank to all the speakers and the participants. Have a nice evening.